Tomorrow. It's a word that scientists think a lot about. Tomorrow is where new discoveries will be made and old discoveries might be proven wrong. Tomorrow is a hypothesis, and there's nothing scientists love more, but every tomorrow has a beginning. There is always a day that tomorrow began. On Big Brains, we explain the surprising research that's reshaping the world around us. But today, we're going to try something new. In a special series we're calling The Day Tomorrow Began, we'll be explaining the historical origins of some of the most important ideas that have reshaped our world, and the through lines that they may carry into our future. And many of those origins happened right here at the University of Chicago. From the University of Chicago Podcast Network, this is The Day Tomorrow Began, a special Big Brain series that explores the past, present, and future of some groundbreaking and breakthrough discoveries. On this episode, from quantum mechanics to quantum technology, I'm your host, Paul Rand. On the last episode of The Day Tomorrow Began, we took you into the past, all the way back to the earliest days of human progress. On this episode, we're going in the opposite direction.
Honestly, I think it's important to appreciate we're at the birth of a new field.
This series is focused on the foundations of scientific fields: biochemistry, astronomy, mathematics. We forget these disciplines haven't just existed forever. They all have a day they started, even if it's in the distant past. And today, we're part of a select club of humans who will be able to say we are actually alive to see the beginning of a whole new field: quantum technology.
Quantum computers and quantum technology overall offered a real paradigm shift compared to what we all use today.
As longtime Big Brains listeners know, that's David Awschalom.
It's a little like driving down the interstate in a fog with low beams.
He's a professor at the Pritzker School of Molecular Engineering, a leading quantum scientist, and the founding director of the Chicago Quantum Exchange. In other words, he's one of the people behind the wheel.
We're moving very fast. We're trying to stay on the road, not able to see clearly what's coming our way. But that being said, there is a glimpse of a few things on the horizon.
Just over that horizon is an incredible future of unhackable computers, supercharged artificial intelligence, and technology that could develop vaccines in the blink of an eye. But as David said, we're just at the start of our journey through the fog.
The emergence of quantum technology is a little like moving from a digital world in black and white to a quantum world in color.
Today, right now, is the day our quantum tomorrow is just beginning.
Within a few years, it's hoped that's IBM's Q System 1 quantum computer, will be cracking calculations that would take a standard digital computer years.
The exciting thing about this field is, honestly, every few days, there's a remarkable discovery somewhere in the world, and many of them in our own laboratories here in Chicago.
Google announced today they've achieved quantum supremacy. So what does that mean? It's a major breakthrough in computer research. Quantum computers are much more powerful than the ones we use today and can solve problems that normal computers often find impossible.
But it's going so well and it's going so quickly, the world will be very different in a couple of decades.
In fact, researchers are already studying how quantum mechanics could lead to breakthroughs in supercomputing, encryption, and even medical treatment.
These are once-in-a-lifetime opportunities, be at the sort of, beginnings of something.
That's Supratik Guha, professor at the University of Chicago, a senior advisor at Argonne National Laboratory, and the former director of physical sciences at IBM.
They were the sciences turning into technologies.
If the car is quantum technology, quantum mechanics is the science that fuels it. So the only way to really understand our quantum technology future is to understand the foundational discoveries in our quantum mechanics past. And many of the most important discoveries in quantum mechanics happened right here at the University of Chicago, with groundbreaking experiments by Arthur Compton in the 30s and Enrico Fermi in the 40s.
I think we're familiar with Enrico Fermi, who moved to Chicago and created the first nuclear reactor. And even in the 60s, Maria Gephardt-Meyer used quantum to explain the atom's nuclear shell structure And most of these people became Nobel laureates for these major accomplishments, and it's a history UChicago should be proud of.
But when it comes to translating quantum mechanics into quantum technology, one of the most important discoveries was...
Well, perhaps the most consequential of these would be our understanding that matter and light behave as both particles and waves, particle-wave duality. A quantum object exists as an extended wave that, upon observation, snaps right into a local particle.
So how does that quantum mechanic help create quantum tech? Well, you apply that concept of neither being a particle or a wave to computer bits.
Today's machines use classical bits, computing, communicating information using digital zeros and ones. But quantum machines use quantum bits, which are called qubits.
And in quantum computing, unlike classical digital computing, where a piece of information is kind of represented either by 0 or a 1 or a string of these zeros and ones, you have a unit device that is neither a 0 or a 1, but it is some superposition between the two.
Yeah, here each qubit can exist in an infinite combination or superposition of zeros and ones. And that allows these qubits to perform multiple operations simultaneously.
In a classical computer, if you're thinking of some computational space and you have to go from one point to another, you sort of go in sequence along a circuitous path. In quantum computing, in a very simplistic way of, stripped of all complications, I kind of think of it where you look at multiple solutions simultaneously and you kind of can arrive at the solution simultaneously without the sequential set of operations. The benefit of that is extreme scale up in computational speeds.
One interesting application that people are thinking about now, which will impact us, is taking magnetic resonance imaging down to the level of a single molecule. Imagine today if a hospital that does MRI scans, typically using 10 to the 20th molecules, could do MRI on one, that we could understand the structure and the functional relationship of proteins inside us. And today we can only do that with a few % of our proteins. It would revolutionize medicine. It would change the way that all of us deal with healthcare. Trying to identify a vaccine, for example, is very hard with a complicated virus that changes shape, reacts to its environment in different ways. How do you model these? How do you even begin to design a pharmaceutical? Could you design a system where you could test all different types of configurations, minimizing real-world testing?
Simulating molecules and so on and so forth. And that is one of the major things that quantum computing might be able to accomplish, right? That where you can exactly simulate a molecule. And so now your laboratory costs in doing Edisonian types of experiments, developing a polymer, for instance, gets reduced significantly.
Another experiment from the history of quantum mechanic discoveries that scales up to quantum technology is...
I would mention the Josephson effect as another defining discovery. It's an example of a phenomenon called quantum tunneling, where a particle can pass to the other side of a barrier, even though it doesn't have enough energy to overcome the barrier. So instead, it tunnels through it, a phenomenon that's only seen in the quantum realm. So this so-called Josephson effect occurs when pairs of electrons tunnel through an insulating layer sandwiched between two superconductors. So scientists call this superconductor sandwich a Josephson junction, and it's used to make superconducting qubits, incredible sensors for imaging, among other applications.
Now, what does quantum sensing mean?
So quantum sensing means an individual qubit, say a quantum bit, instead of trying to protect it, we can expose it to the world as incredibly sensitive atomic scale sensors. And they can measure temperature, electric, magnetic fields, even the vibrations of a single atom. So right now, we're placing them in single cells to monitor biological activity and on satellites to improve GPS. So it's an incredibly important area of the field.
Superposition is one of the underlying quantum mechanisms by which quantum technology is built. Entanglement is the other.
Entanglement is an odd thing. It has no analog in our classical world, but it means that these qubits can share information even without a physical connection.
You can entangle qubits at one end and the other through, let's say, a fiber optic network.
What makes entanglement so important in quantum technology is it could allow us to create unhackable communications.
You would be able to send tamper-free information protected by the laws of physics, that if somebody tampered, you would know that they've tampered it.
But how?
Quantum physics says that the act of observing something changes it. So if someone were to spy on a quantum-encoded financial transaction, we'd be able to tell, simply because peeking at this information changes it. We're seeing prototype quantum-secure communication networks on metropolitan scales that are being built today using entangled qubits. Now remember, entanglement is a special connection that doesn't require a physical contact to safely transmit information without fear of eavesdropping or identity theft.
You could set up things like voting systems, for instance, where it would be tamper-free. Nobody would be able to eavesdrop on it.
The financial sector is looking at quantum technologies and trying to understand how their business challenges can benefit from them. Because one of the challenges in the financial sector is when someone performs a transaction, they want to be sure that nobody has extracted the information along the way, copied it, put it back, and then you receive it. And how do you know that you haven't received information that somebody has copied or tampered with? So they would love a technology where that will be virtually impossible. There's no way to extract the information without changing it. It's ultra secure. It's interesting to look at the financial sectors around the United States and see that they're also growing quantum groups. JP Morgan Chase has an extraordinary group of quantum scientists they've hired. So does Goldman Sachs. Places that a few years ago you might not have thought would be building quantum technology programs.
The challenge there is in getting data rates high up. Classical communications occurs through very high data rates. So far, quantum communications, from whatever estimates we've done, the challenge is going to be in enhancing these data rates while preserving the secure nature of the communications.
And if you think about more personal applications, I think some of these that we're talking about are kind of, for lack of a better word, the industrial scale. Is there a point where you would see this would actually trickle down and be something that individuals will be able to utilize, such in the way as we're using things in the digital world today?
Sure. As we just discussed, I think using quantum secure networks for online purchasing and even in-store shopping is likely to replace credit cards and provide massively improved security. We also think it's conceivable that atomic scale quantum sensors may be used to help provide advanced home diagnostics and more personalized medicine, much like we're seeing with COVID antigen tests. Imagine being able to use quantum sensors and microfluidic chips to perform diagnostic measurements and using your cell phone to transmit the data and receive the results quickly.
If it isn't obvious by now, quantum technology will completely revolutionize our world.
I think these are very complicated problems, even how you efficiently deliver packages, how you assemble aircraft. A 777 has over 3 million parts, for example, in a Boeing aircraft. How do you assemble them in the right order? How do you make that process much more efficient? You could use trial and error, or you could use an optimization algorithm in a quantum machine and solve it and know exactly the right order to do the assembly. I think we'll see lots of impacts on society as we learn more and more about the potential of this technology and get informed as to what are the most challenging problems with our partners. Where do they need help? And how can this quantum technology be used to assist?
We really don't know today what the real applications for quantum technologies might be. We should not have that hubris. There's going to be some application that comes out just out of the blue, and we don't know that yet. But new things will come out. The same thing happened with semiconductors. The same thing happened with light emitters. And it'll happen in quantum. I am convinced something is going to come out of this.
Imagine where we'd be today if we hadn't invested in the groundswell of activity that led to Intel, right? That led to fabrication centers in the United States for building chips. Where would we be economically? Where would we be in terms of jobs for all of us? So now we're at the birth of this field, a little bit like the birth of the transistor, and we need to make a decision. Do we join the global race? Do we lead the global race? Or do we sit on the side? And I don't think anybody would argue we should sit on the side, so this is where we are today.
But how do we actually get our quantum technology car over the horizon? Well, that's after the break. Like we said at the beginning, quantum technology is an entirely new field of science, which means that the first step to making significant progress is integrating it into our research infrastructure.
So there are many departments around the United States and the world with fantastic physics programs doing fundamental quantum science and traditional engineering, electrical engineering, civil engineering, mechanical engineering. What has not been done is thinking about the birth of this new field where you need to integrate these different disciplines: computer science and physics, mathematics and chemistry, electrical engineering. Train students in a very different approach and think about working at this intersection between discovery and translating these discoveries into engineering devices for society.
But here at the University of Chicago, one school is leading the way to our quantum tomorrow, the Pritzker School of Molecular Engineering.
The Pritzker School of Molecular Engineering embraced a really unique approach to engineering that's problem-driven rather than focused on academic disciplines. And 4 important societal problems were identified to launch this engineering program, one of which was quantum engineering. And this societal problem-driven approach gave us an opportunity to hire over a dozen faculty across physics and engineering, chemistry and materials science, aimed at developing this very new field and training students with a fundamentally cross-disciplinary approach. And in addition, what was new about this approach is we realized we really couldn't make meaningful progress alone. And we created the Chicago Quantum Exchange, a hub for advancing this area of science and engineering between universities across the Midwest and around the globe, with our 2 Department of Energy national labs and over 36 companies. So this combination of now over 150 scientists and engineers has really made Chicago a leader in the field. So I would argue you're right. The founding of the PME at Chicago has played a major role in this endeavor.
Another institution that's affiliated with the University of Chicago that's at the forefront of quantum technology is Argonne National Laboratory.
Argonne and the University of Chicago, together with other collaborators, are setting up what we hope is going to be one of the first major, quantum network test beds where you could come and test your devices, the real life conditions of, moisture, temperature, things shrinking and expanding, traffic going over fiber optic cables, giving rise to vibrations, just stuff like that, right?
The first problem PME and Argonne are trying to solve is,
well, I believe in a word, it's workforce. Where will the quantum engineers come from to really drive everything we've been talking about? Estimates from independent parties suggest the U.S. will need tens of thousands of quantum engineers just within this coming decade. So we've launched some new initiatives with the National Science Foundation, offered graduate students partnerships with companies. We've started certificate programs to train existing industrial scientists and engineers in the quantum field. But that's going to be a limit. How do we bring a workforce into a new field, reach out into much more diverse communities, get much more engagement in science and engineering to meet these numbers? That's a challenge, and I believe that's going to ultimately be a bottleneck in this process.
So that's the area where I think, Argonne and the Pritzker School of Molecular Engineering are taking a lead, and that's where the Chicagoland area is taking a lead.
And it's because of 3 simultaneous events happening. 1, a wave of retirements in the United States in engineering and companies. 2nd, the changes in immigration laws. And 3rd, the global competitiveness of the field, and that countries around the world have fantastic programs now. And there's less of an impetus for people to come to the United States. So when you put this together, it's making it very difficult for these companies seeing these retirements to come up with a viable plan to not just fill these jobs, but build a quantum engineering program. Again, when you look at nanoelectronics, one advantage the United States had was Bell Laboratories, IBM Research, HP Labs, right? DuPont, Motorola, companies that had hundreds and hundreds of physicists working at this interface. They're largely gone today. And so we literally, in the quantum world, live in a flat world now in terms of workforce and competition. So the model has to change in the United States for us to lead. It's not going to be the same as the past because the conditions aren't the same. So I view that as an incredible opportunity to get a much more diverse workforce.
Another problem is materials.
There's a lot of work going on in materials development for quantum technologies. Having a physics idea and a neat experiment in a lab somewhere is great, but how do you make it into something that's going to excite someone outside the quantum field so that it's scalable, it's cheap, it's compact, you can put it on a table and say, push this button and it works?
Right now, materials tend to come from different research groups around the country. What many of us feel is important is to standardize the process, build a foundry where researchers around the country will have access to well-characterized, pristine materials that can be used for their specific application. Their tests and quantification of these materials will be fed back into a national database for companies, university researchers, and national lab researchers to analyze, study, improve, and distribute.
Of all these things we're talking about, it's clear that the US government, the Department of Energy, is looking at what's happening in the world, whether it's China or other places, and saying this is becoming a really pretty hotly contested race. And I wonder if you can talk about, well, what is the quest to do from a global perspective, from a competitive perspective, and how is the US government, the Department of Energy, investing in that, and where does Chicago fit into this mix?
Well, the key to driving a lot of this area of science and technology is collaboration. And one of the nice things about all of these partnerships is it's put Chicago in a very competitive mode to collaborate for national centers in quantum information science and engineering. And as part of the 2018 National Quantum Initiative Act, passed by Congress, the United States decided to fund 10 national centers, half by the Department of Energy and half by the National Science Foundation, to really bring people together to focus on major challenges. And at the end of the day, because of this environment we built here collectively in this region of the country, 4 of the 10 national centers are established in Chicago and Illinois. It's an extraordinary accomplishment. And that's really helped move the field. It's driven things like building test beds for companies, like the Chicago Quantum Network. A 124-mile network spanning the city and the suburbs of Chicago, linking Hyde Park, the university, Argonne, Fermi National Accelerator Lab. That's brought in companies like Toshiba and JP Morgan Chase. For example, right now, working with these companies, we're transmitting over 90,000 quantum bits a second between Hyde Park and Argonne National Lab. So over nearly 40 miles, distributing entanglement. So I think things like this also will help build a quantum supply chain. The country's going to need to produce sensitive photon detectors, compact cryogenics, high-speed electronics. And I should say also, I think, in terms of competition, this will help us move discoveries from the lab into industry and change the landscape of the field. When you think again about the transistor invented in the mid-1940s in a lab, and today, billions of transistors sit on a single chip that we carry in our phones, thanks to industry's scaling of their manufacturing. So with quantum technologies, we need to think about working on scaling, of course, with fundamental advances in material science and fabrication and physics. So these linkages, these centers, these collaborations are really key. And I think that's what's going to make us competitive in the world.
And if you look now, even as we're coming up on 10 years for PME, do you look at this and say, particularly in the quantum area, there's been some notable advances? And if so, what would you point to?
Faculty and students here have developed schemes to create and control quantum bits in commercial semiconductors using the spins of single electrons. So electrons are used today commonly in our technology, but not so much their spin. It's the inherent property of every electron, like its mass or charge, and we can manipulate these spins to hold quantum information. And what the students here have done is achieve the longest lifetime of electron spins in semiconductors. And it's amazing because these are commercial off-the-shelf wafers, the same ones that are revolutionizing electric cars and LED lights. There's been amazing theoretical work in the last 10 years here that's identified and opened an enormously new region of materials that can host more robust quantum bits than anyone imagined through theoretical modeling and prediction. Students and faculty have designed and synthesized new classes of quantum bits, but now from the bottom up, growing them, if you like, with molecules. This was work done in collaboration with Dana Friedman at MIT and faculty here. This offers the opportunity to engineer quantum bits at the atomic level for application from sensing to memories to communication to computing. It's a very, very different radical approach. People here have also developed powerful paths for binding quantum sensors to biomolecules. We mentioned a little bit about this before. Literally decorating sensors with biomaterials they can attach to specific locations in a living cell. And I would say, even at the far end, researchers here in the PME have demonstrated control of quantum sound at the level of single phonons, not photons, but phonons, which you can think about as a quantum of vibration in material. And they've created small entangled networks with microwaves and superconducting qubits.
If we look back and somebody 50 years in the future is doing a period like we are now about the day tomorrow began, and people say, well, here's some of those changes starting in 2022 and beyond that utterly transformed the field and the impact of quantum. What do you think some of the things might be going forward that folks would look back on and say, boy, these things happened and it really pushed our field forward?
No, that's a fantastic question. Sort of what will be discontinuous discoveries that will accelerate the field? Well, making qubits more connected, being able to hold on to quantum information for longer times with less error will be important. But one obvious one that comes to mind, say for quantum communication, will be the successful creation of a quantum repeater. That will launch global quantum networks of entangled states. So a quantum repeater is a device that boosts a signal as it travels from one place to another. And without quantum repeaters, a message might just die before it reaches its destination. So creating these devices is a fascinating challenge at the interface of quantum science and device engineering. Again, looking at something changes it. How do we repeat information? So I think when we go through that barrier, and I believe we will, you will see the birth of quantum networks globally. In the same way that today's internet is working because we have repeaters. You and I are talking with one another if we were, across the world, fried light going through optical fibers. After 50 or 60 miles of going through a fiber, because there are impurities in the glass, the light starts to attenuate, need to boost it, send it again. They're all over the world for today's communication. Building quantum repeaters will change this field.